All right, trends. We were talking about some of our periodic table trends last week on Wednesday during our extra lectures. One of our trends is ionic radius. A lot of these trends use concepts like effective nuclear charge ZF that we were talking about last class as well. So for ionic radius, this is the radius of ions as opposed to the neutral species that we were looking at last week. So if we have a positive or a negative charge, that'll affect the size of our ionic radius. For cations are much smaller than neutral atoms. The reason for this is we were looking at thinking about our shells of electrons, right? And when we get cations, the cations that most commonly form are caused by ripping away that complete outer shell. If we completely get rid of a whole shell, we've basically shrunk it down one row on the periodic table. In addition, there's also higher effective nuclear charge. That's that Z effective, because we've lost a couple of electrons. So hopefully, kind of a no-brainer. You take away electrons and it gets smaller. For ionic radius with anions, anions are much larger than neutral atoms. We're adding electrons. And we have a lower effective nuclear charge. Since there's more negatively charged electrons, there's more electrons counteracting the positively charged force in the nucleus. We talked about effective nuclear charge with our atomic size for neutral species. So as we're moving left to right on the periodic table, we're adding protons on the inside. That increases the effective nuclear charge, and that causes the electrons to get pulled in slightly more. Here we're doing the opposite thing. We have a lower effective nuclear charge, so that electron cloud can balloon out a little bit more because of the extra electrons. And these images, the species on the left is the neutral, and the one on the right is the charged. There are a lot bigger differences than I was expecting to see, despite not adding like a complete extra shell, just completing that shell. There's also isoelectronic ions, so different elements with the same number of electrons. That's the same total number of electrons. So things that are isoelectronic, for example, would be in this table below, things that have the electron configuration of argon with 18. Try the red one. Red one. So we've got sulfur. That's going to gain 2 electrons, get 2 negative charge. It's got an argon configuration. Chlorine gains 1, becomes argon. Potassium and calcium lose 1 and 2 respectively to become like argon. So all of these have 18 electrons, like argon. And we can see their ionic size, or their ionic radius. Since they all have the same number of electrons, the thing that's different is the number of protons. Adding more protons, just like moving left to right on the periodic table, we're changing our effective nuclear charge. And so they get smaller. It's the same principle for working on neutral species, moving left to right on the periodic table. It's that Z effective charge. And this would work for things that have the same electron configuration of krypton or neon or other things. All right, ion size. Choose the larger atom or ion from each pair. We've got potassium, fluorine, and calcium or chlorine. So think about what's happening when we're changing from the neutral species to the charged species. And for the third one, think about what the different properties of those are. All right, potassium or the potassium ion, which one is larger? Yeah, it's potassium. What happens when we change from potassium to the potassium ion?
It loses the outer shell.
Yeah, it loses an outer shell, or its most outer shell. So K plus lost its only valence electron, and it loses a layer, if we think about it like a cake or a onion. What about fluorine or fluoride? Which one's bigger? Yeah, it's fluoride. Why is it fluoride? It doesn't gain a layer, but it gains an electron. And the extra electron causes a decrease in effective nuclear charge. So that allows the electrons to expand out a little bit. They're not as strongly pulled into the nucleus, so they can be a little bit further away. How about the calcium ion or chloride? Which one is bigger? I believe this one is chloride. Yeah, this one would be chloride. It shows up here. It's an effective nuclear charge reason. So chloride has 17 protons. The calcium ion has 20 protons. They have the same number of electrons, though. So it's the same principle. We've got a lower effective nuclear charge. The electrons are going to be able to balloon out further. Questions about any of these three? Great. Another periodic trend is ionization energy. This is the energy needed, an input of energy needed to remove an electron from an atom or ion in the gaseous state. The gaseous state part isn't like super important. Probably we can think of them as not being in the gaseous state, and it probably works about the same. This is always going to be positive. It takes energy to remove an electron. So for a metal plus an ionization energy, it goes to M plus 1 electron, and that's the first ionization energy. So the IE for ionization energy and the 1 for first. And you can do it again. So you can start with this M plus, hit it with some more ionization energy, a beam of electrons or something, and pop off another electron. I think we just talked about the first ionization energy in this class. The principle for the second ionization energy is probably similar, just a little less clear. So the first ionization energy decreases going down a group. The valence electron is farther from the nucleus. It's easier to pull it off. It's easier to pluck it away. Or you could think of it as it's less strongly held. Since they're a magnet force, the further the magnets get away from each other, the electron being further away from the nucleus, the easier it is to remove it. And it also increases across a period. So left to right. Our effective nuclear charge increases. So that's a stronger attractive force. So this is the opposite of atomic size for neutral species. And another thing that may be worth noting, our noble gases are the highest energy. Our alkali metals are the lowest ionization energy. Alkali metals love to lose their electron. They'll do it basically for free compared to all the other elements. Our noble gases, however, have that beloved noble gas configuration. They are super stable with all of their electrons filling out whatever their outermost shell is. They really don't want to lose that electron. And so that's why they're so comically high compared to the rest of the elements. Here's another way of looking at it. We'll see a couple more of these 3D charts today because the person that made the book really loves them. So this is just the ionization energies. You can see they increase from left to right and bottom to top. Hydrogen's kind of in a weird spot. All right, for the ionization energy, we can predict the higher first ionization energy, for some of these at least. Our first one, we're looking at tin or iodine. So thinking about which one of these least likes to lose an electron. That'll be the one with the higher ionization energy. In this case, it's iodine. Iodine's very close. If we want to anthropomorphize it, it's very close to becoming xenon. It just needs to gain one more electron. It's so close to, going positive at the casino. It just needs one more win. and we're going to hand it another L. It's going to be very upset. Versus somebody who's already down $500 at the casino, if they lose another 100, I mean, maybe they would also be devastated, but they could also just be accustomed to losing. I don't know. Another way we can think of it for these two in particular is that we have tin. Tin's a metal. Metals tend to lose electrons. Nonmetals tend to gain electrons. So this is going with tin's tendency and going against iodine's tendency. For calcium or strontium, strontium, we want the one with the higher ionization energy. In this case, that's going to be calcium. Because it's smaller, the electrons are closer. Since the electrons are closer, the magnetic force is stronger. And then carbon or phosphorus. For carbon or phosphorus, it's hard to tell. We have competing trends. On the one hand, carbon is smaller, and so it's going to be harder to remove an electron in that way. But phosphorus is further to the right. It's closer to getting that electron configuration that it so wants. And so in that way, it's harder to remove from phosphorus. So this one's probably a toss-up. I would guess that it's carbon. Let's look at this 3D table. Hey, look at that. It is carbon. Carbon's slightly higher than phosphorus. This one, a little bit sort of a toss-up. Like if we had compared silicon and arsenic, right, we would have gotten it wrong. I just guessed because carbon's really small. So that one we just guess because we have competing forces. And then the last one, fluorine and sulfur. We do not have competing forces here. This one is fluorine. Fluorine is both smaller. And so it's this calcium versus strontium thing. But on top of being smaller, it's also further to the right. It's closer to being a noble gas, and so it's really not going to like having an electron yoinked away from it. Questions about any of those? Great. There are some exceptions to our trends in ionization energy, the first one at least. Keep forgetting to turn Do Not Disturb on. It generally increases from left to right across a period. There is an exception between groups 2A, so things like beryllium, and 3A, like boron. Boron actually has a smaller ionization energy, first ionization energy, than beryllium. So that's counter to what we expect. And the reason for that is that boron is losing a 2p electron. 2p electrons are higher in energy. And so it's easier to remove. If we draw orbital diagrams for both of these, they're both going to have a full 1s. They're also both going to have a full 2s. Beryllium being at the end of the 2s, the end of the s block is not going to have any electrons in the p block. Boron, however, will have 1 electron in the p block because it's in that first spot in the p block, that far right group for our main group elements. Since it just has 1 electron there, that makes it relatively easy to remove. Compared to removing this paired electron in this full S shell. Another exception occurs between our groups 5A and 6A. So nitrogen has a half-filled 2p sublevel, or subshell, as I'm accustomed to calling it. That makes it especially stable. They're synced up. They're all pointing up. Thank you. Oxygen, however, has 1 more electron. And that 1 extra electron makes it easier to remove. If you were on a field trip, going to a conference or something, and you've got a room with, all your rooms have 3 beds in them, and you've got one room where there's 1 person in each bed, and you've got one room where there's 2 people in one bed and 2 empty beds, and you said, hey, we've got an empty bed somewhere else, and you tried to get somebody to leave from either of these 2 rooms, chances are it's this down spin electron that would be the first one to go. They'd be like, yeah, I'd love to have my own bed. I'd love to not be here. Unless they're, sleeping with their besties or whatever. So that would be a way of relating it to that upside down triangle hotel, chemistry land, whatever. So adding this 1 electron in makes it a little bit, I don't know if it's necessarily less stable, but it's certainly more stable going to this synced up configuration versus leaving this synced up configuration not as easy. If you want to take off another electron, so if you want to go to the 2nd or 3rd ionization energy, it gets harder each time. For sodium and magnesium, sodium has a very low first ionization energy. Sodium actually kind of likes to lose 1 electron, right? That's what it needs to become like neon. If you then go to take a second one off, you're taking it out of that stable electron configuration, and that's why the 2nd ionization energy here is so massive, because that's a core electron. It's taking away that stable neon configuration. For magnesium, we have a higher first ionization energy compared to sodium. That's giving it the electron configuration of sodium. The second one, by comparison to sodium, is really small. And that's because we're moving from the sodium configuration to the neon configuration. And that's especially stable. And then moving out of that neon configuration, again, huge ionization energy. That's not the pen. This is the pen. I can do better than that. And then the other thing is we're pulling off extra electrons. So it's going to get to be more and more energy every time. We have a higher effective nuclear charge because of the previously removed electrons. And the electrons are going to be closer to the nucleus because of that higher effective nuclear charge, also making it harder to remove them. Here's a table. This table shows us on the left side the different elements. This is our period 3 and our ionization energies for the 1st through 7th electron removed. You can see in the blue, these are just the valence electrons, the outermost shell, the n equals 3 shell. And our core electrons, the first one is shown in this pink section. So you can see a trend along here, increasing ionization energy because it's a further electron removed. So it's going to be bigger than, removing the 6th is going to be worse than removing the 5th, or harder. And for our ionization energy just before that, it's relatively small compared to its downstairs neighbor. So like for magnesium, this second ionization energy, all of these are the last electron in the valence shell. So removing your last valence electron compared to your second to last is easier. There might be some comparison that I'm missing there, but relatively easy compared to other ionization energies. Is this our last trend? It's not our last trend. Maybe it's sort of our last trend. Okay, electron affinity is the opposite. Opposite of ionization energy. Sort of. Or exactly. We're gaining an electron instead of losing an electron. It's usually negative. Energy is released when it gains an electron. Some alkaline earth metals and all noble gases have positive electron affinity, meaning that you have to give them energy for them to accept the electron. Why is that? Where are the alkaline earth metals? What group are they on the periodic table? They're 2. What does their electron configuration look like? Some number S what?
2.
Yeah, so like beryllium would be 2s2. Magnesium, 3s2. Where would that extra electron go if you add one more electron? Where does it go? Yeah, it goes into the p subshell. All right, sublevel. We're adding to the p sublevel since S is full. And the concept is the same for our noble gases. Our noble gases represent a completely filled valence shell. And the next electron that you would add goes into a higher principal quantum number level. It is a less regular trend than some of our other trends, though. electron configuration, or electron affinity, sorry, decreases, becomes more positive. You get more energy as you go down. You put more energy in. As you go down the group. Other groups don't show a trend. It generally increases. I'm confused about the negative positive language, my bad. It generally increases across a period. It becomes more negative, more exothermic. Group 5A has a lower electron affinity because the next electron must pair. The previous one would be filling out the electron configuration. All right, so the electron configuration I wrote there, this red one is that one that has to pair. Our highest electron affinity, the most wanting to gain an electron, is our halogens, because that puts them where? Disneyland? Six Flags Magic Mountain? Space? Purple? Where does it put them? It's the noble gases. Yeah, it makes them like noble gases. Electron affinity, here it is. Lots of numbers, what do they mean? More negative number. Means more energy released. It wants to gain the electron. It's willing to pay to have the electron absorbed. If it's a positive, so greater than 0, that means that you have to spend energy to add the electron. Questions? I expect at most one question about electron affinity on your exam. At most. All right, some properties of metals and nonmetals. These are some of these things are things that we've talked about possibly too much. So things about metals. Metals are malleable and ductile. You can bend them into shapes. You can pull them into wires. They're shiny and lustrous and reflect light, at least if you shine them. In comparison, our nonmetals are brittle. Diamonds are made of carbon. They're very hard. That's not exactly the same as brittle, but if you got one of the other nonmetals together, like sulfur, that would probably also be brittle. They tend to not be very reflective in comparison to metals. Metals conduct heat and electricity because of the way they are. Nonmetals don't really do that. Metals we're missing a word here. Most oxides are basic and ionic, whereas for our nonmetals, our oxides, things with oxygen on them, are acidic and they're molecular. Molecular because oxygen's a nonmetal. Nonmetals with nonmetals is molecules. Metals form cations. They like to lose electrons. Nonmetals form anions. They gain electrons. And metals tend to be oxidized. Nonmetals tend to be reduced. Our last ionic, or our last periodic trend, is metallic character. How much of a metal is it? Is it a true metal, or is it not as true of a metal? So the ideal properties of a metal were like stuff that we saw on the previous page. This one is easy enough, though, if you just think about how easily does it lose an electron. Or where are the metals? On the periodic table, the metals are on the left. Our nonmetals are on the right. So the further you are to the left, the further you are into metal territory, the more of a true metal you're likely to find. The further you are to the right, the more likely you are to be one of those gosh darn nonmetals. You're not going to have very good metallic character. Metallic character also increases down a column. Another way you can think of it is if you're over here on the right side of the periodic table, our nonmetals are at the top, our metals are at the bottom. They're also, if you're further down a group, you're more likely to lose an electron. Your electrons are further out, you have a larger atomic size. Easier to yoink one of those electrons away. Questions about metallic character? A bunch of these periodic trends you can just memorize as opposites of each other. So something that you might do is a little flashcard with an arrow up or down, left or right. A couple of those, or you could write them out on a page, figure out which ones are the same, which ones are opposites, and you could just memorize a bunch of them for general purposes. Here's a chart showing a cross-section with phosphorus, phosphorus being a metalloid, maybe? No, it's a nonmetal. What am I talking about? That's just the cross-section. So on the left to right, metallic character decreases from sodium to chlorine. Chlorine's definitely not a metal. And it also increases moving from nitrogen, a nonmetal, down to bismuth, definitely a metal. Here's another way of looking at it. Wow, it's the same thing, just with more stuff on it. All right, on the basics of the periodic trends that you know and love, choose the more metallic element from each pair. Our first pair, we have germanium and tin. Which one's more metallic? Tin is more metallic. It is a metal. Germanium is not a metal. That works here. It's also further down. The further down you go, the more metal-like you are. How about gallium? Where are you, gallium? There you are, gallium. Gallium or tin. For people on the recording, I'm shrugging, right? So gallium, further to the left, more like a metal. However, tin further down, more like a metal. So we've got competing forces. Or competing trends. Could be tin. Put a question mark with tin. How about phosphorus or bismuth? We just talked about it. Bismuth, it's metal. And boron or nitrogen. Which one's more metallic? It's boron. They're in the same row. So the ones that are further to the left, closer to the metal side, are more metallic. Questions about any of those in particular? Cool. Here's a summary of periodic trends. There it is. I don't know why they didn't just put in like left and right arrows, but when you're moving down a column, for atomic radius, it's increasing. Metallic character, increasing. If you're moving across a row left to right, atomic radius decreases because of that change in effective nuclear charge without adding on another layer. For metallic character, it decreases because the ionization energy increases. So this might be a helpful thing to reference from your book, if you have the book, or you can just steal it from the slides. I don't care. Questions about any of the trends stuff?